Next, we need to calculate what is shear stress occur for the velocity profile of polynomial velocity profile. So previously we already know that we have two equation for shear stress. One is tau equal mu 2u over delta, which come from the Newton law of viscosity, and tau equal rho u square d theta dx, which come from the von Karman equation. So from these two equations, to calculate shear stress, I advise you to use equation from Newton's law of viscosity. It is because in Newton's law of viscosity, the value of tau here is fully developed. So if we see terms from von Karman equation, it is rho u square d theta dx. The term difference of d theta over dx here showing that this equation is not fully developed. It is mean that we cannot use this equation for further investigation. So please remember, use the shear stress equation from Newton's law of viscosity. So what we need to do is we substitute the value of delta from our previous answer here, which is delta is equal to 5.48x over Reynolds number, and then we could get that tau is equal 0.365 mu u over x and Reynolds number. Please be advised that the value of delta equal 5.48x over Reynolds number here is only for velocity profile parabolic profile. For another velocity profile, the delta here needs to be calculated again, and the value is not 5.48x over Reynolds number. Next, we are going to calculate these two items, local drag coefficient and drag coefficient. So local drag coefficient usually symbol as C subscript small d, and drag coefficient is C subscript capital D. So the difference between local drag coefficient and drag coefficient is, local drag coefficient is drag coefficient that occur for one local point. For example, we have point 1 here. So the calculation is only for this point. The drag coefficient for only this one point is called local drag coefficient. And drag coefficient here is the total drag coefficient for the whole object here. Please be advised that for calculation of drag coefficient here, the influence of area must be included in your calculation. I will show you later. Okay, let's go for local drag coefficient CD. As we know in previous calculation, tau is 0.365 mu u over x Reynolds number here, and we know that from the common equation tau for local drag coefficient, tau is equal to CD 1 over 2 rho u square. So if you see here, so this equation is actually similar with the common equation of drag force is equal to CD times 1 over 2 rho AU square. As I said previously, local here means the calculation is based on one single point. So the value of A here is not exist in this equation. So we have two equations of shear stress here. What we need to do is we equalize these two equations, these two value of shear stress, and then we could simplify the value of CD is equal to 0.73 over third Reynolds number. Please try this at home. For drag force, as we know that force can be calculated by multiplying shear stress and area. So what we do here is we do the integral process of shear stress times B times dx. B is width of our thin flat plate, and the egg is the length in x-axis. So B times the egg will represent the value of area. So tau A could give us force. The integral limit is from 0 to L. So 0 is the origin and L is the maximum length of our flat plate. We substitute the value of tau that we get in previous slide. So this is the value of shear stress that we get, and B is the width and the egg is the distance in x-axis. We replace the value of Re with its common equation, which is rho ux over mu, and then we simplify this equation. We have two terms of x here, 2 mu and u here, so we could simplify it into these terms. We do the integral process from limit 0 to L, and finally we could say that drag force can be calculated by using this term, which is 0.73 times u, sed rho u mu, sed L and B. And this is the calculation for drag coefficient. Previously in our slide, we know that drag force is equal to CD 1 over 2 rho A U square. So we rearrange this equation, so we have 2 times FD over rho A U square, and we know that A is length times width, and we could say we substitute the value of FD that we get from the previous slide, so we could write CD is equal to this. And then we simplify this term, and finally we try to represent Reynolds number, and we could get the CD is equal to 1.46 over third Reynolds number. So here, because we are calculating a flat plate, so instead of we are using rho ux, we could use rho ul, which is L is the length of our plate. Normally, we could say that 0 is the origin of our plate and L is the maximum value or the maximum length of our flat plate. Okay, for your tutorial, I hope you could do by yourself at home to find delta, boundary layer thickness, CD, local drag coefficient, and local coefficient C capital D here for all velocity profile. What I showed you previously is the calculation for delta CD here for parabolic profile, means for u over u 2y over delta minus uy over delta square, and the answer is 5.48x over Reynolds number, 0.730 over Reynolds number, and 1.46 over third Reynolds number here. So I hope you could try at home to get the value of delta and CD for the velocity profile of this and other type of velocity profile. Then here I show you one answer for Blasius exact solution. So I will explain about this in my next presentation. Please subscribe this channel, C23 Classroom channel. Thank you for watching.